Thank you very much. So this is joint work with Maaike and my two supervisors, Anne Jort. And so let me start with, in one slide, try to explain to you an overview of what I did. And if there's one thing you need to take away from this presentation, this is it. So as most of you probably know, there is a correspondence between definitory monad and algebraic theories. And also another correspondence has been expressed lately, a few years ago, between distributive laws and something called composite theories. This correspondence was first explored by Chang on the level of Lavery theories, and then translated to how it should correspond for algebraic theories by Pierre and Staton. And this correspondence was what allowed Maaike to express her famous no-go theorems for distributive laws. So with this setup, I was wondering, wow, we have distributive laws, and nowadays there is another notion that has gained traction, which is called weak distributive laws. I was wondering, could I extend this correspondence to the weak setting? So that was my setup. So I thought I would dive into this first correspondence, try to understand it fully, and then translate it. And I realized that it was only one part of this correspondence was in fact fully proven. So I decided to finish it. And then when I realized that it was quite some pages, I contacted Maaike, and we made a paper together with both had proofs. So this is the setup. I've included a slide on monads, but I guess most of you are probably familiar with what those are. But also, here are two examples of monad, like release monad or posted monad for non-determined. For monads, there is the notion of monad algebra, and in this talk, we could talk a lot about distributive laws. So for those of you that have never heard of it, indeed, it goes back to Beck. And the prime example of a distributive law is the fact that this multiplication distributes over addition, right? This was like a categorification of that fact expressed through monads, with the two monads being present for multiplication and addition are monoid, so the list monad for monoid, and the Billion group monad. On the other side of this first correspondence, there is algebraic theory. So most of you are also familiar with it. Just to write notation, I will write arities of function symbols in superscript. For every algebraic theory, there's also an infinite algebras where it's an interpretation that satisfies all equations. And for every algebraic theory, there is a free forgetful adjunction where we take the equivalence classes of terms. And if we compose this adjunction, we get a monad called the free algebra monad. And this allows for this first correspondence that I mentioned about. An algebraic theory is a presentation of a monad if we have an isomorphism of monads, or equivalently an isomorphism between the category of algebras. Right. So this first isomorphism relates the two monads on a syntactic level, and the second one on the semantic level. And yeah, right, this is something that we usually do where we consider equivalently a list as a monoid term and so as a joint assimilative term, etc. Right. So this is the setup, but there is one more preliminary that I need for that I've used in this paper, which is term rewriting. So I don't know if this one you're familiar with. So let me just have one slide. So there is two types of rewriting that I will use, which is called string rewriting and term rewriting. Where the first one can be seen as like a special case of term rewriting where every function symbol has an arity 1. And so a string rewriting or term rewriting is just a set of rules with the left-hand side and right-hand side. And when we have such a rewriting system, there is three properties that we are usually interested in. Those three properties are termination, tells you that every rewrite sequence terminates. And the two others are two variations of something called confluence, which one local version and then a global version. In the local version, you ask that if you start with the term and have two distinct rules applied, then you might rejoin them. And when I write this double head arrow, it means the reflexive and transitive closure, so 0, 1, or more steps. So here, local is when you do one step peak, and confluence is when you have multiple steps. And the reason why we care about those properties in particular is that when you have both termination and confluence, you have something called normal forms. A normal form is a term that cannot be rewritten anymore. And termination tells you that those normal forms exist, and confluence tells you that they are unique. And so computationally, it's very interesting. And here are like two main results that tell you how to derive those properties. So confluence is very hard sometimes to calculate. to know if it exists. But thankfully, there is the Newman's lemma that tells you that if you have termination, then local confidence is enough to entail global confidence. And to know if weak local confidence holds, there is a nice criteria, which is we have something called critical pairs, which are basically all the culprits where local confidence could fail. So it's all the times where two rules overlap with only single, like here, A, B, and B, C. And in that example, so this is the string reference system here. In that example, this is not confluent because here this critical pair doesn't converge. You cannot join them at the bottom. So this is some preliminary on graph writing. So now let me tell you the other side. So this is what the preliminary is. Now tell me the other side of distributive laws. Distributive laws are well known, but maybe you have never seen composite theory. So let me flesh it out. In the same way that the basic distributive law is multiplication over addition, on the other side, this will be the same thing with the theories. And in fact, it corresponds to the theory of the monoid abelian groups. Then when you put them together, you obtain the theory of rings. And the theory of rings is both theories plus two distributivity axioms, right? Left and right distributivity. And composite theories is like the axiomatization of this behavior of what we have here. And so basically, thanks to left and right distributivity, every time you have a ring term, you can just distribute everything and always end up with an abelian group term with inside his the variable substituted for a monoid. So when we put that into a definition, if you have two theories S and T contained in a bigger theory U, we say that the term is separated if it's of this form, so a T term with S terms inside. So here the notation X means that X ranges over all the variables in T. And when we have two separated terms, we say they are equal modulo ST if they are essentially unique in the sense that if we take their equivalence classes in TS, so remember, so those are the free algebra monads, so now we work with equivalence classes, that their TS equivalence classes are equal. And what this means that we can basically compare the two separated terms on the two levels, right, on the T level and the S level. And this allows us to have the definition that the composite theory is a theory where every term is separated, can be separated, so I mean at least one separation. And if you have two of them, two separations, they must be essentially unique, so they must be equal modulo ST.
So this is like multiplication means like thing that you should be here.
Exactly. Yeah. Exactly. And indeed, in ring, right? In ring, we have this equality that 0 is the same thing as 1 times x minus x times 1. But more than just this equality in ring, we have that this equality, in fact, falls on the two levels, right? X minus x equals 0 and x times 1 equals 1 times x. So now we have that we have everything.
We're back.
And
yes, but I need to make it the full screen one. So it's this one. That's the wrong tool. And it's the, or maybe it's that one.
Nice.
And there, and then still, those rooms are going. Reporting is happening, I think. Top running, yep, cool. Then time insurance.
I'm back. I'm back. Cool. We're back. This was the ad break. So in that direction, when we start with the composite theory, we can build a distributive law that, given the term in FC, just take the representative and give the separation of it. And this is well defined because of this equality modulo ST, because of this essential uniqueness. And checking that this is a distributive law is just tedious but straightforward. So that was the existing direction. Now the other one, suppose we start with the distributive law. We need to now build a composite theory. So how do we do that? We just join both theories, but we add like this third set of equations, which are the distributivity equations. So how are those defined? It's every pair of terms that are representative of an input and output of lambda of a distributive law. And with that defined, then we claim that the lambda is a composite theory, TNS, T after S. And we tried first to prove the thing like directly by hand with induction on terms and induction on the proof tree to prove both properties of the composite theory. But that's where we hurt ourselves and realized that some graph rewriting was much needed. So let me show you the tools that we need from rewriting to have this proof. So first of all, given the u lambda term, we have defined in the first function, which is what we call type, that gives the string of term string in this set made of letters S and T's that tells you how nested the operations are, right? So you have like S terms and S operations and T operations and S operations, etc. So in that case where we have F in S terms and G in T terms, and that u lambda term with some coloring, we realize that the type is STS, so blue, right, blue, green, blue. And then we introduce also this notation where we write the type of it. We take the equivalence class to mean when we put the equivalence class bar at the right place every time. So we only use this notation when it's unambiguous, of course. And the idea is that given the term u, to separate it, we first look at it in its equivalence class, and then we apply all three natural transformation as much as we can until we reach a point where it's no longer possible, being either TS, T, or just S. And this really resembles rewriting with the normal form, right? So we've defined, we have given it a name called functor rewriting system that appeared in some form or in the literature under the name rewrite category. But the functor rewriting system is just the alphabet are functors and the rules are natural transformations. And we take the functors just as like strings of alphabet. So if there is an equality between functors, we don't allow it. And like, so we have one in our case, right? The letters are S and T's, and the three rules that we consider are lambda and both multiplications. And why do we give it a special name? Is because now we're like, with functors and natural transformation, there is one more data that we can make use of, which are when diagrams commute. So we give those two variations of functions where we add like the word commuting afterwards, and this represented also by this little arrow and circle arrow. So when the same diagram has confluence as before, but the same thing with the commuting diagram. And both results that hold for term rewriting systems also hold in this setting. So when you have termination, local confluence commuting, you have confluence commuting, and to have local confluence commuting, it suffices to look at critical pairs. And with that done, like our system that we have, it's a bit straightforward to check that it's both terminating and confluence commuting. For termination, any technique that you like, we choose polynomial interpretation, where we can give a higher weight on the S letter than on the T letters, and then every rule being strictly decreasing this ensure termination because N is well founded. And for local confluence, there is exactly 4 critical pairs that we need to consider, which are those 4, which are exactly the axioms of lambda and of monads. So it's really funny how like this was very natural to consider. It's really funny you've probably all noticed that like a lot of very often category theory axioms even make sense from a purely like rewriting point of view, right? If you are an SST and you want to find 2 ways to end up in TS, there's those 2 natural ways, and you ask them to commute. So yeah, this proves it's terminating and confluence terminating. And now that we have that, we can take define a function that's separated, that separate any u lambda term, where we take the equivalence class and take any path to normal form, because we know that now we know that those are equal. And once we are in the normal form, just take any representative of it. And this way you have the first part, which is that every u lambda term can be separated. But we have more than that. We have not like any paths to normal form are equal. And this is useful for the second part, which is that if you have 2 separated terms that are equal, they must also be equal modulo ST. And now that we have all these tools, the proof is tedious, but just again straightforward, where we do an induction on the proof tree, and we prove that at every step, at every equality, we just separate both sides with our function set, and we have equality modulo ST. So every study is straightforward. Those are like the complex cases, but again, just it follows by a sequence of equalities. The annoying part without these tools of rewriting was the transitivity case, because if you started, if you try to do the proof without rewriting, you were like, okay, I want to do an induction of the proof tree, and at every level, I want to prove that the equality modulo ST is preserved. So the problem is that you could go from U1, which is separated, to U2, which may be unseparated. Like if you have an equality of separated elements, U1 go U3, U2 might be not. And if you're like, okay, I separate every level, you might separate U2 differently in both directions, right? Here above and here above. But now this is straightforward. So that was it for the proof of this correspondence. There is one last result, which is that in both directions, we have that the composite monad given by the distributive law is presented by this composite theory. And in this direction, there was also a proof in Srat thesis, but we just updated it with a shortcut that maybe some of you know. This notion of lambda algebras. When you have a distributive law, it's something that is both like a triple, which is both an S algebra and a T algebra. And this theorem, we'll look at it a little bit more, because it tells us that if we have a distributive law, it's usually distributive laws are useful because it's a sufficient criteria to know that the monad's composed, right? And this theorem tells you that, okay, if you have that, we already have even a presentation of that monad. But there is just a slight problem. U lambda, as it was defined, was nice for the correspondent theorem because it contained all distributive equations. But in practice, we don't want infinitely many of them, right? So we want to find a minimal axiomatization of U lambda that is that has the same congruence generated as U lambda, right? In the basic example of multiplication over if we were to start with the distributive law lambda and construct U lambda, we would contain all those distributive equations, right? Even like basic one as x equals x or x equals x plus 0. And we have expressed a way to determine to showcase minimal sets when a minimal set can be served as a minimal axiomatization. To do that, let's just employ some terminology of layers. So if we have a term which is made of an S part and a T part, the layers is a pair of natural numbers where it's the number of operations. So the number of S operation and the maximum of the number of T operations. So visually, if you write a tree, if you write a term as a tree, it's really the number of layers that you have visually. So for example, here, that term has a 1-1 because it's one multiplication operation with every subterm being one abelian group operation, and here is layer 0, 2 first. And what this allows us is those two lemmas that give us this minimal representation. So we consider only the equations that have left-hand side of this shape, where it's one S operation with inside only one of the arguments being not a variable and being exactly one T operation. And for the right-hand side, we just pick one of them. And this gives a term rewriting system. And if this is terminating, then we have the same congruence. So this was the first result that we obtained, that like if it's terminating. So now here is a second lemma that tells us one type of scenario where this termination is unsure. So if all the rules are of this form, so left hand side has layers 1, 1, and the right hand side has layers something 1, and some linearity requirements, then we have termination. And let me show you 3 examples where we have this this setup applying. So in the case of lambda of the multiplication of addition, this holds. So this is how we end up with only left and right distributive equations. But also many other in the literature that we checked. So here are 3 examples that we picked out of randomly. And in every case, we obtain a very elegant axiomatization of the composite monad. But just consider indeed only equations that have a left-hand side of layers 1, 1, right? So only one operation of each theory. And right, this would be the way that people usually sometimes even define distributive laws, right? You just look at the algebraic side, just write one distributivity equation and say, we have a distributive law. But this is something very dangerous to do, right? Even though it's tempting, and this has resulted in many of the errors in literature about wrong distributive laws. So this is a small setting that tells us sometimes we can do it, but we have to be careful. And some comment about the criteria that we have found. If it's terminating, then we have the same concurrence. Here is a small example that tells you that it's not always the case. Like that if termination is not there, then the conclusion might fail. So this is a good counterexample that is built upon one of the famous, like a basic exercise when you have a TRS class, which is that if you have a single rule, AB goes to BAA, this is a non-terminating TRS. The reasoning being that if you start on AAB, then you are stuck in a loop. And we just realized that we could extend a little bit that counterexample, that TRS, to obtain a counterexample that shows that this gives a distributive law. We have adapted it to obtain a distributive law. And if we only take the equations, the distributivity equations with left-hand side layers 1, 1, then there is one distributivity equations that we cannot derive. So this showcases how why termination might be important. But I'm not going to go too much into the detail of what this distributive law is. Just an extension of that can be wrong. So that was it for my presentation. In summary, so now we have a fully fledged, full proof of this correspondence in the category of sets between distributive laws and composite theories. And what was really interesting, I found, was the proof strategy that we came up with. And then we gave a criteria when a minimal axiomatization can work. And for future work, there is, of course, we give one example of when this termination is unsure, so we can look for more criteria. But nowadays, all distributive laws that we have encountered fall under the one termination scenario that we've expressed. But we can now that this correspondence has a full proof, we can look at how to extend the correspondence. For instance, like what I said in the intro, work on weak distributive laws. But there is also make sure that everything works when we add non-finite monads. So if you know this is on the algebraic side, it's when you allow function symbols to have infinite arities. In the case, a main example being, for instance, the power set monad or the ultrafilter monad. We can change the base category set. This is kind of difficult to do. Some people work on monads, not sets. There are many examples of that. But very, very quickly, if you try to change the base category, you very quickly end up working with Lavery theories. And just like the original correspondence that was on the level of Lavery theories. And this is very more obscure what's happening, which is the nice aspect of this correspondence in set. So there is weak distributive laws that are worth looking at, or also when you have not only one sort, so multi-sorted algebraic theories, what happened there. So these are full leads for extending the correspondence further. The one I'm mostly interested in is the one that I started with, so weak in the weak setting. But that's it. Thank you for your attention. That was my presentation.
You're both fluent in both the diagrammatic and the symbolic ways of seeing algebra. Very good. There was many years ago, there were some thermoregulatory people who were using category. I hadn't heard of them for a long time because of the fragmentation that happens in the algebra in the academic world, but it might be worthwhile trying to
do you know
find out.
Do you remember one of the author?
I'll think about it.
So the danger is that if you look rewriting and category theory, there is also an extension of term rewriting, which is graph rewriting.
Yes.
And nowadays, graph rewriting is done almost entirely in category theory. So most results you will find is about this framework, and that's also something that I've been working on.
One criticism, right?
Yeah.
You have Greek on your sweatshirt.
Yes.
The singular of criteria is criterion.
Ah, sorry. Yeah. Thank you. Yes.
I have maybe a naive question. But concerning the concept of composite series,
Yes.
can you represent that, say, group rings as a composite series?
Yeah, that's
So
that.
in fact, twice you need to compose twice.
What do you mean by compose twice?
You mean you start with groups and groups. So you create your rings, and then you compose again this group to get group rings.
I've never heard of group rings.
So actually, this you consider linear combination of group elements with partition being formally ring element.
Yeah.
And then you organize a natural ring.
Yeah, that might be a composite theory. Do you have distributive equations in that case?
Yeah.
Okay, then yeah, that might be a perfect candidate for a composite theory.
Where you extended Newman's number and to this functional rewriting system. Is that like a trivial extension, or is that something you want to go on?
No, it's very straightforward. It's basically looking at the proof of Newman's lemma and realizing that the proof is can be summarized in one diagram. In fact, every part of the diagram commutes. Yes.
There's a notion of a theory being cumulative theory, and it is where the function symbols they kind of commute in the sense. But then you can have one theory that commutes with another theory, in the sense that you can have take these terms from each set of these kind of terms, function symbols, and then you have equations that kind of So how much does this relate to this notion of distributive law, that you have this kind of commutation between the function symbols? I know, of course, will be many variables.
How different?
So how is there kind of
I'm not sure. I'm not sure to see what you are talking about. You're talking about when you just can commute the symbols.
I mean that you will have a matrix amount of variables x, I, j's, and then you have so if you have in one signature you have a function symbol if, and in the other signature you will have a function symbol g, and then you apply f g to the matrix, and then you have g f to the matrix, and to be accommodative means that these end results should be e. So I'm wondering if this is related to this, but
probably the category theory is related to the numbers in the previous talk. I think the category theory associated with this is the kind of commutative strong related.
Yeah, that's.
But in which setting? So you work when working matrices, you've seen that thing?
So we can talk about this.
Yeah.
So when you are writing these finding critical function,
Yes.
you had only monad multiplication law.
Yeah.
But somehow these unit laws are in I don't know how they are in because when you go to decompose, just to drop one of the unit laws, right?
We don't consider without either of those, because in fact separating the term can be only done by swapping every instance of S and T in the wrong order, and then we have the tower of S and tower of T and tricking it. There might be an interest in consider an older rewriting system where we have the units, but then of course we would lose termination because right, you can add symbols now instantly in time. Because then maybe interesting in another degree.
These after rewriting systems,
Yes.
can they be used to like reverse engineer? Can they kind of, suppose you have some functions in that transformation structure, can you kind of reverse engineer what coherence conditions are sensible ones by demanding like the nice properties of the function rewriting system?
Well, I'm not sure to see what you mean by reverse engineering.
Like suppose you have some structure and you expect that there might be some natural coherence associated with the structure out of the natural transformation.
Okay, some equality between natural transformations.
Yeah, right.
Yeah.
Like, can these be reverse engineered? Like, does the fact that like if you demand that there is that these make both the rewriting system that has all the properties that you spoke about to somehow give you coherence condition.
So whenever you have a system with functors and distributive laws, and natural transformations, and you have some equalities between the natural transformation at hand, you can transform that into a rewriting system. And the interest of it is a bit like one major application of TRS, of term rewriting systems, is to decide, it's to work when you have other equational, it's called equational reasoning, but it's equational theories, algebraic theories. So to know how, if a certain equality is derived, you can just compute both normal forms if they exist, and that gives you the equality. There is a correspondence between equality in the equational reasoning and convertibility in the rewriting system. So you might have the same thing in any setting that you want in natural transformations, and you just put your equality that you start with, and you can maybe automatically deduce some theorems.
But related, by the way, how MacLane proves the coherence theorem on a systems system that so it's related. These systems are related to coherence.
Oh, didn't know. Thank you. Very good. Now,
So, excellent talk.